We are calculating the electric field due to a uniformly charged thin ring. Let us calculate the electric field due to a uniformly charged ring having a total positive charge of Q. Let R be the radius of the ring. One of the easiest ways to calculate electric field would to take a field at a location along the axis of the ring, which is the line going through the center and which is perpendicular to the ring. As shown in the figure, the total charge contribution of del E is due to its component along the x, y, and z axis respectively. As shown in the figure is del Ex, Ey, and Eg. Also, delta E represents the electric field of a ring having an angular size of del theta. The center of the ring is chosen to be origin. As we see that we are cutting the ring into small pieces. As we cut into small pieces, we take a small piece as a reference as shown above, which has an angular length of del theta. The origin is the center of the ring. Also, the location of the ring can be described in terms of angular displacement theta, where we saw in the figure that theta was equal to 0 along the x-axis. Now we resolve all the components in terms of integration variable theta. We first find del E along the z-axis, electric field due to a small piece, and integrate it from 0 to 2 pi, as 2 pi is the circumference of the ring. Now we find the distance, which is object location minus source. As the object location is in the z-axis, our x and the y components are 0, and the source location is r cos theta and r sin theta. We get r, that is displacement, which is equal to negative r cos theta and negative r sin theta, and z. So we find the modulus of r, which is by squaring the x, y, and z component respectively. We get r squared plus z squared is equal to 1/2. Now we know that r cap is r by r modulus, which we get negative r cos theta, negative r sin theta, z by r squared plus z squared to the power half. Also, we know electric field due to a charge delta q at a distance r from the charge will be 1 by 4 pi epsilon delta q by r squared. As calculated in equation 1, we had r is r squared plus z squared to the power 1/2. So we substitute that in an equation of delta E. We get 1 by 4 pi epsilon delta q 1 by r squared plus z squared to the power 1/2 whole square, whereas we get delta is equals to 1 by 4 pi epsilon delta q by r squared plus z squared. We know theta is equal to 2 pi, which has a charge of q. So delta q will be q times del theta by 2 pi, as delta q is the charge obtained in del theta. So replacing in equation 2, we get delta E is equals to 1 by 4 pi epsilon q by del theta by 2 pi r squared plus z squared. Now we find the direction of delta E. So we multiply it with r cap. We get 1 by 4 pi epsilon q del theta by 2 pi r squared plus z squared times negative r cos theta negative r sin theta z by r squared plus z squared to the power 1/2. As we know that the x component and y component resolve to 0, we only have the electric field along the z component. As I mentioned earlier, we integrate the delta E from 0 to 2 pi. So we have electric field along the z-axis that will be 0 to 2 pi of delta E to the power delta Ez. So as we integrate, we get 1 by 4 pi epsilon q 2 pi z by r squared plus z squared to the power 3/2 as a constant, and we integrate del theta from 0 to 2 pi. So we get, from integration, we get this 2 pi. As we cancel 2 pi and 2 pi, we get electric field that is 1 by 4 pi epsilon qz by r squared plus z squared to the power 3/2.